All right, how we doing, everybody? Doing okay? All right, what's the update of the week? How's the classes going?
We're learning about capacitors, I think, for Professor Liu's class.
Dr. Zeus? How's that going? You guys understand how to use them? Kind of not. It's okay, no worries. So I think one of the things I wanted to reassure was how how to get the actual voltage from these capacitors, correct? So if I were to have, I don't know, I'm gonna draw some circuit, plus minus, maybe some, I don't know, switch, correct? Then what do I want to do? I want to do a resistor. Yeah, let's do a resistor. Capacitor, right? Is that good? Is that something familiar you guys are watching? Correct? And then let's just do, how do I want to do this? It's going to be V, I don't know, call it V1 or something like that, V1. And then this right here is R, correct? This right here is a C. Is that good? Everyone familiar with what's going on? Now let me just do something. So I'm gonna quiz you guys in a little bit. That's why I kind of drew it like this, because I saw it from your guys' problems. Let's just say I have another circuit over here, plus minus. I'm gonna call this one V initial, right? And then, okay, call this one V final. Is that good? And let's just say that this circuit right here is initially connected like this. All right, so I'm connecting this right here. T is less than 0, correct? Is that good with everybody? So, without thinking too deep, if I have this kind of circuit, correct? Right, if I have this voltage, right? Let's just say it's VI, initial, right? If you want me to make you guys happy, I'm gonna put 1 volt. Does that make you happy? Just 1 volt? Is that good? If I have 1 volt going here, right? After a very long time, correct? What's the voltage at the capacitor? 1 volt? And why? Yeah, because... Yep, we're charging the capacitor to 1 volt, right? And now it's got 1 volt, right? So our initial voltage right here, I'm going to call this one, I don't know, VC, right? At T is less than 0, correct? Before we start switching, it's going to be 1 volt. Is that good with everybody? Is everyone following what we're trying to do? This is going to be on your homeworks. And now I'm going to do something funny. I'm going to start switching it down here. Now I'm going to short that, okay? And then this, I'm going to disconnect it, okay? Now it's at T is greater than or equal to, okay? Now we're using this circuit, okay? We just charge this capacitor, right? There's 1 volt in there, right? Is that good? And now I'm just gonna throw a random number, 5 volts. Oh, howdy. You can place it over there, just on the table. Thank you. So let's just say we have 5 volts, correct? So I have one battery, right? One battery that's like 1 volt, and then I have another one that's at 5 volts, correct? I'm switching, correct? There's 1 volt in that capacitor, right? But now you got to start describing what this is going to look like, all right? So this is where I want to start rederiving this, because there's an equation I want you guys to memorize. So the first thing I'm going to do, let's see, draw my little guy. You guys like the little guy? Start going up the hill, correct? And I'm going to do a current like this. I, is that good? And then if I'm going up this hill, right, I have this battery. I'm calling it V final, correct? V final, right? Plus to or minus to plus. I'm going, here's minus plus, right? I'm going up the stairs. I like reiterating this. Do you like how I'm just saying up the stairs, down the stairs? Does that help you like visualize what's going on? Yeah, that's actually what my old professor taught me. He's like, let's not think about letters or variables. Let's think about stairs, potential, okay? Plus minus, right? We got the resistor, right? Going plus to minus. I'm going down the stairs, correct? Which is IR. Is that good? And then for capacitors, plus minus, the current always goes like this, right? Is that good? And then minus VC is equal to 0. Is that everyone understood with what's going on? Is that good? All right, so the next thing I'm going to show you, and let me just click that right there, is remember what the current in the capacitor is? Remember that little equation? I is equal to C dV over dt. Is that good with everybody? And then we can start replacing our variables into our thing. So we have this right here, right? And then we have this voltage right here. I'll tell you how to deal with that soon. What's his name? Yeah, I'll show you. Next page. I want to see if I can derive this from memory. So we got V final, right? That's the final that's the voltage I want. Okay, I'm switching it from this battery to this battery. All right, is that good? Minus, and then I is equal to C dV over dt, right? But then there's an R, right? RC dV over dt. Is that good? Then I got also another VC right here is equal to 0. Is that good? And then what is this right here? This is going to be VC, right? Do you understand why? Because the voltage over here is going to be plus to minus. What's the voltage drop? Just VC, correct? VC minus ground. Is that good? All right, now we've got to start solving our equation. We have our VC right here. We have our other voltage. Let me see if I can tell you this without making it too complicated. I want this guy and this guy together. Let's just do this. VF is equal to, let's see. Oh, I want to do this. Let's try this. VC minus or plus RC. Okay. And then, what do you call it? This right here is DV. C over dt. Is that good? I wonder if I'm getting this correctly. I think I want to show you what's going on. Because I want to do a, what do you call it, equation, where, let me show you what I'm trying to do. I want to prove this. Let me show you this. Did you go over this over the notes? Yeah, this is what I was trying to show you guys. Because there's an equation I want you guys to know. Is this right here? You guys are gonna use this for all your homeworks. Is that good? So what did I mess up? Let me see. I'm gonna walk through this because you guys like PowerPoint, or you guys want someone to actually try? Does he actually try, or does he just point at this?
He was showing how it was correct a little bit, explaining it.
Okay. So that I did this good correctly. Here's VS2, right? That's our V final, right? Well, he has it this minus plus plus, correct? But we did plus minus minus. Is that good? Right? And then let's see, what do we have right here? So I think the difference between what we did right here and then this right here is just the way we called it, because this is our V final, right? This is our final voltage we want. And then this right here is our RC, and this is our V, or whatever initial charge was on that capacitor. Is that good? So then let me see what he tried doing over here. He tried getting in terms of this. Okay, I think I know what he's trying to do. Let me see. Let's see. dV dt. You're crazy. I think I know what he's trying to do. VF over RC is equal to VC over, what do you call it, RC? Is that what we want to do? RC plus dVC over dt. Does that look kind of similar to what he's got right there? Because this B final, this B right here is this V final, right, over RC. Is that good? And then this AV, right, is our, what do you call it, the voltage in the capacitor, right? What is V? That's your initial voltage, right? I'm trying to solve this for you guys, but I'm not liking this. Let me see. But you see what I'm trying to show you guys? So basically, you got to get this this differential equation right. It's gonna turn into something like this. All right. So do you actually know what this is translating to? Let me just mark this down like this. Where v of I don't know v final of t correct. That's what we're trying to find, right? Is equal to v initial, right? Is that good? V initial or V settling? Is that what it is? No. That's what we want to get. Hold up. Okay. V infinity, right? Plus, I'm going to explain this one by bit because I don't like the way that I'm seeing this. E to the minus t over tau. Okay? Let's dissect this, okay? Let me show you. So this infinity, right, is actually t to when we're taking it to infinity, right? So this is after infinity time, right? So can we call that our final voltage? Is that correct? Plus, and then what's V0? That's our initial capacitor, right? V initial, right? VI, is that good? Minus that whatever final voltage we want, correct? V final, e to the minus t over tau. Is that good? And then this right here, well, it's not V final, it's just when t is infinity, right? If t is equal to infinity, right? If it goes to infinity, right? Well, let's see. What happens to this term? If we're going to infinity, so this is e to the negative infinity, right? What is that? A very small number, right? 0, correct? So what are we left over with? V final, right? Does that make sense? So technically it's not really V final, it's just regular voltage. We're trying to figure out what's going on. So after t goes to infinity, it's going to be V of t is equal to V of f. Okay? Is that good with everybody? But then when we have t is like finite, right? It's very less than infinity. Then we're going to have to rely on this equation. Okay? Is that good? Who wants to start doing problems? What problems do we want to do? So let me see who I have. I got Dr. Zoo's homework here. Which one looks funny? Who's my Dr. Zoo students? What do you guys want to do? This one? Number 3? Find the voltage across the capacitors. I got you, no worries. So we got to find the voltage across the capacitors in the circuit under DC conditions. Okay. You'll realize why I chuckle. Don't worry, you guys will get there too. AC circuits? Yeah. You'll see how fun it is. Well, the reason why I chuckle is it's pretty, not elementary. You got to know what's going on. V2. Don't worry. I'm writing exactly what's going on, okay? 50, 10, right? This is C1, 30, plus minus V1, and then this is 60 volts. Okay. Find the voltage across the capacitors. Oh, wrong one. There you go. How do you want to start this? Draw a ground. Is that good? This is 0 volts, right? What's the voltage over here? If this is C2. I don't know. I'm calling this one VC2. Is that good with everybody? I'm just labeling some stuff. So let's see. And then right here, we can just call this one VC1. Is that good with everybody? Okay. So what do we know about DC conditions for a capacitor? Remember, a capacitor is just 2 plates, correct? And then if I have, I don't know, some current I, right? This is an open right here at DC. It's literally just an open. It's just 2 plates. Does that make sense with everybody? So do you think these circuits are scary? Maybe, not really. Just replace them with opens. What's another way we can rewrite this? Like this. Then let's put the capacitor there. That's our 10 ohms. Plus minus. 50. Just put a terminal right there. Does it bother anyone if I do this? Is that good with everybody? What's the current in here? I1. 0, right? So what does that mean about VC2 over here and this voltage? What does that mean when I is equal to 0? There's no voltage drop, right? So if the voltage drop here is nothing, right? It's 0, right? What's the voltage here? VC2. Is that good? So what does that mean about this resistor? Doesn't mean much. Doesn't do anything. All right? So now the next thing, VC1, right? What does this look like? Voltage divider. Yeah? Is that good with everyone? VC1, right, is equal to whatever our input voltage is, right? Let's call this one, I don't know. Was it 60? Yep, 60 volts. Right? 60 volts. And then that voltage drop here, plus minus the voltage drop of, what's our resistor? 30? 30 ohms, correct? Let me see. I'm going to do this, just this notation, all right? Okay. And then I'm going to do R30 plus whatever this resistor was 10, R10, right? And then plus R20. Is everyone understanding what I just did there? All right, so there's another way to do this. So this right here is to calculate the voltage drop, all right? So if you wanted to calculate, well, this one, you'll have to add these two resistors together. Does that make sense? What I'm trying to show you? Solve for VC1. Good? So what did I mean? So if this right here was our, what do you call it? 10 ohm resistor, right? And how do we solve for VC2? Or VC2 right here. Is going to equal the 60 volts, right? Plus these two resistors, right? I'm just going to write it. 30 plus 10, right? Is that good? All divided by 30 plus 10 plus 20. Boom, we solved it. Any questions about that problem? Just simple KVLs. I don't like this, David. And yeah, just do regular KVL. Is that good with you guys? What's our next problem? You guys know how to do this one? Yeah, just parallel. Well, you got these parallel capacitors. You got these ones in series. Just like resistors. Find the voltage of an inductor. You guys have you guys talked about inductors yet? Not really, not yet. Just starting. You'll realize there's a similar equation for that. Under steady state DC conditions, find I and V in the circuit. Well, I'll tell you this. An inductor is just a piece of wire. You want to make an inductor with me? Let me show you. No, wrong one. I don't know. I'm just, see this wire right here? I'm just going to create a coil. Is that good? So, and then you start realizing, oh, if an inductor is just a cable, is just a coiled wire, right? What does that mean about our grounds in our buildings or this right here, right? That means you can start, what do you call it? Creating like a current, or what do you call it? Creating some type of impedances, right? When you have these kinds of like mishmash current, like curvy wires. That's why they try to tell you to keep it straight so it doesn't like cause noise to go through this. because you'll realize inductors are good at coupling noise. Anyways, what other problems do we got here? Guys like that one? I'll tell you this, inductors are the same like resistors in terms of adding them in series and in parallel. So shouldn't be too difficult, right? Let's see what else. You got the switch, right? The switch in the circuit has been closed for a long time and it opens at t is equal to 0. Find Vt for t is greater than 0. Let's solve for this one. You guys want this one? Pretty tough circuit. All right, I'm going to draw it. Don't worry. Plus minus 60 volts. And then we close it. 10K. And what do you call it? Got it 2K. Plus minus V of t. This is 40 microfarad. Okay, sounds good. Find the voltage. Is that good with everybody? So it said, well, let me see what the problem says. It's been closed for a long time. Okay, I got that wrong. Okay, so initially, right? It's closed, right? So I have 60 volts right here, right? Then I have 60 volts. Well, let me show you this. At infinity time, right? What does a capacitor look like? It's just an open, right? Right? So that means another way you can do this, right? Plus minus 10K, right? 2K. What does this look like? Voltage divider. Pretty cool, right? So I'm gonna what's this one gonna be? Let's call it VI is equal to 60 times what's this? 2K, right? Over 12K. Is that good with everybody? That's equal to, let me see, these K's cancel out, and then this 2 cancels out with this to give you 6. 10 volts. Is that correct with everybody? So initially, there's 10 volts in here, right? All good? Now we open it. So now let's do the following. Is that good with everybody? What's the voltage over here initially? Right? What's the current in here? In that resistor? 0, right? So what does that mean about this resistor? Ignore it, right? Is that good with everybody? So now what does this look like? Let me see, this is 2K. And then we're trying to solve for V of t, right? Looks like that, what do you call it? Vt is equal to V final. What was that equation again? Let me see. V final plus V initial minus V final e to the minus t over tau. Is that good with everybody? What's our initial voltage? VI. The capacitor. 10 volts, right? After a long time, right, the current's going to go like this. I'm just calling it, right? It's being discharged by that resistor, our iPhone, right? What's the voltage after a long time? 0, right? We're just emptying the tank, right? V final is equal to 0, right? Plug and chug. VT final, right, is 0, right? 0 plus, what's our initial voltage? 10, right? Minus 0, right? And then let me see. E to the minus t over tau. What's tau? RC, right? But what resistors are going to be based off this current? Just that resistor, right? Remember how tau is equal to, call it RC, correct? It's the only resistor that we have in this circuit. 2K, right? And then we have this capacitor, correct? Which is at 40 micro, right? 2K and our 40 micro. What's that equal? 80 kilo, and micro make milliseconds. Is that good with everybody? And then what's our V final or VT? 10 e to the minus t over 80 milliseconds. You guys like that plug and chug? What is this going to look like if I were to tell you to draw it on your exam? I don't know. He might ask. I don't know. 3. If I were to do the following. Here's time, correct? So this circuit, right? It was closed, right? And we had 10 volts right here, right? So initially, oh, there we go. This is V. 10 volts. Is that good? Now I'm going to do the following. So let's see. If I were to do, here's V of t is equal to 10 e to the minus t over tau, right? But I want to do 10 e to the minus 1, correct? Is that good with everybody? I'm going to call this one where tau is equal to 80 milliseconds. Is that good? Where's the voltage over there? Calculator. I don't know if my calculator is going to do this. How do I do 1 minus? No, that's not right. I don't like this. How do I do this? This to the power of minus 1. 1.71? That times 10? No, I don't like that. What the heck? E to the minus 1. Well, there's another way of doing this. Let me show you this calculator. Clear. 10 divided by E. There you go. I wonder why I wasn't getting it. 3.67 volts. So what I just did was just do 10 divided by E. Is that good with everybody? Right? 6.7 volts. So then you're trying to draw this graph, but I'm just going to give you the guys the cheat answer right here. 3.67. Is that good? Oh, sorry. Thank you. Right, that, right? And then you're going to do another time constant, 160 milliseconds. You're going to start realizing, right? It's going to go all the way down. And then what happens if I tell you to calculate after t is equal to 5 time constants, right? So if I were to do the following, V of t is equal to 5 tau, right? 10 to the e to the minus 5. What's that equal to? Let me see. I don't like this calculator. We'll try. E to the power of minus 5? No. To the power of 5 minus. There we go. Ah, that's what I was supposed to get. Is that good? Yeah. So 10 times, I don't know, 0.0067 is equal to, let me do this, times 10. We're getting some funny numbers here, y'all. 0.067 volts. What does that look like? I don't know, very small, right? So you guys see this exponential? So if I were to just draw for you simple, like that, right? After 5 time constants, it starts to look like it's just 0, it's discharged, right? But after the first time constant, right, we lose almost like 60 something percent. Is that good with everybody? Actually, what is this right here? 63? No. 10 to this. Let me do this. 10 minus 3.6 is equal to, where's my calculator? 10 minus 3.6. Yeah, 64%. So we're losing about a lot of like voltage after that first time constant. Does that make sense with everybody? So if you wanted to have a rule of thumb, we're losing about after 1 tau, right? What do you call it? We lose, what's his name? V of t is about, I'm going to do an estimate, is about RV times 64%. Or not 64%. The other way. 36%. Is that good with everybody? Any questions about that? We can do this homework now. What's our next problem? Inductors, we'll talk about that another day. Let's skip this one. Let's go to, what's his name? Where's his homework? Is this it? No, this is his home.
Only the first one can be done. That was the one that has capacitors. The other ones that have to do, so only 5.6 can be done.
5.6?
No, 5.16 or 5.6. In a 75, that's right. It's in the book, right? You have a little book.
This right here?
Yeah.
Okay, let me see. 1628. So inductors, 33. Let me see. Is this it? That's the right problem, correct? You want to do it? We're already here. All right. Let's do this. So it says, problem 33, correct? So if we have the following, I'm going to draw the circuit. Plus minus V0, V0, V initial, whatever you want to call it, R1, 2, why is it doing 2, 1, got some weird arrow, R3, R2, C, plus minus VC. So after being in position 1 for a very long time, so I'm going to make story time, right? T is less than 0, correct? For a very long time, right? The switch is changed to position 2 at time is equal to 0, T is equal to 0. All right? So let's think about it. No thinking. Or let's just, very basics, okay? We have a resistor, right? We have another resistor, right? What's the capacitor after infinity time? There's no voltage, right? It's just empty. Just an empty bottle of, like, just think of, like, I don't know, this tea right here that I have. It's already, it's empty. There's nothing to do, all right? So V initial, right? Because that's something we know is going to be 0 volts, okay? Then it says, we switch it now to 12 volts. Okay, we switch it now to this position, right? So, there we go. All right, is that good? Let me rewrite the circuit because I don't like seeing all this clutter. 12 volts. And we have this right here, R3. I'll just put this in just in case, R2. And see? Is that good with everybody? It says determine, okay. Determine the initial current, or actually no, the current before we switch and the current and the voltage before we switch, right? So before we switch, okay? So T is literally less than 0, all right? We're looking at before, okay? What's the current in here? 0, right? It's just an open. And then the voltage is also 0, right? Boom, done, okay? No thinking. It says it wants to know right at that instant, okay? What is the current and what is the voltage? So I just closed that switch, correct? So this is empty, correct? It's an empty bucket of water, right? So what's the, T is right at 0, right? What's the voltage?
I forget which one it was, but you can't instantaneously jump to your volts can't instantaneously jump. Is that for capacitor or is that for inductor?
So for the capacitor, what's his name? It's a bucket. It's gonna have a level of water, right? We're thinking about the water level, right? Think of that as the voltage. Current, you can instantaneously throw water into that. Is that good? So now, the current, right? What's the instantaneous current? I don't know. You tell me. We have this I right here, correct? Call it I1 or something like that. And then we also have, let me just do this. I don't want to do this. Let's just do I2. Is that good with everybody? I'm calling this an IC. Is that good? KVL, right? Well, do I want to do KVL? Maybe we'll have to. So let me see. Yeah, let's just do KVL. What's the current going in here? I1, correct? Current from this source. What's the current leaving? I2, right? And plus IC. Is that good with everybody? What's I1? 12 minus whatever this VC is, right? All divided by that resistor. So if I were to do the following, 12 minus VC over R1, right, is equal to VC over R3 plus, what's IC equal to? C over D, VC over DT. That sound good? So you know what I'm thinking? Sounds crazy, but let me see. Because I wonder if we can cheese this pretty good. I wonder. Because you can also do the following. If we wanted to do this, IC, right, is equal to I1 minus I2, correct? And then just solve for that instantaneous current going through here and the instantaneous current going over here. Actually, let me tell you this. The voltage here is 0, correct? Initially, right? What's the voltage over here? 0, right? So what's the current in here? 0 and 0, right? So let me show you this. I2, right, is equal to whatever this right here is, V plus minus V minus, right, over R3, right? But V plus is 0, right, and V minus is 0, right? So what's the current? Yeah. I2, right? Or whatever, I2 is equal to 0, correct? So what does this tell you? We have I2 right here, right? It's gone. So what does that mean about IC instantaneously? Is it equal to I1, right? So what's I1 then? We got this 12 right here, right? And then we got our initial 0 volts, right? So I'm going to do I1 is equal to 12 minus 0, right? Over, what's R1? R1 is 30K. Let's see. I can't calculate. Calculator, 12 divided by 30. So we got 40. We got 0.4 milliamps. 0.4 milliamps. Is that hard? No?
Better after you count the
Huh? Yeah.
It'll
Well,
be better after you count the odds.
it feels good, right? Why? Why was this I2 gone? Because the voltage here was 0, right? Let's not forget our fundamentals, okay? Even I forgot a little bit. I'm like, wait a second. There's 0 here or 0 here. That means no current, correct? But there is a current because the current right here is generated. 12 to 0, right? Divided by that resistor, current. All the current is being sucked into that initially, okay? So what page was this? Let me see. So this was page 4. Page 5. Page 6. So let's see. Now I want us to figure out, why is there a star over here? We'll figure that out. The current after infinity time, all right? So can everyone agree that it's going to look like this, plus minus 12 volts? R1. Okay. Is that good with everybody? So after infinity time, right? What's the current here? Like now we have this circuit, correct? What's the voltage or the current through this capacitor after infinity time? 0, right? Why? Because it's an open. It's just 2 plates. After infinity time, it's not doing anything. Boom, done. Good. What about the voltage after infinity time? We just said this was an open, right? Voltage divider, right? BC is equal to 12 volts times, what do you call it? R3 is 60K. And then we got 60K plus 30K is equal to, let me do this, 12 times 60 all over 90K. The K's cancel out. Then that's going to be some number, right? What's this going to equal to? 8? 8 volts? Is that what we got? Let's do it. 12 times 60 divided by 90. Yeah? Don't worry, I trust you. Guy, I gotta double check. We're going through this homework pretty fast. VC at T. Right now we're just trying to describe this equation. Is that good? So let's just say we have the following circuit. Plus minus. I'm going to use a different color. 12 volts. R3, R1. Capacitor, okay? We just said initially VI, right, is 0, right? What's our final voltage? 8, right?
Oh, no, I can't see that, but yeah.
Oh, let me, don't like this. There we go. We just said after this is closed, right? That's going to be 8 volts, right? Is that good with everybody? So how do I want to describe the voltage right here, VC over T, or VC of T? Is equal to V final plus V initial minus V final over e to the minus T over tau. Is that good? But now here's the thing. The current, right, is being, okay, remember, let's do one thing. I gotta tell you this. I1, right? And then, I don't know, I'm just calling this like this. I2 and IC, correct? And we just said IC. Oh, actually, how did I label our equations first? I want to keep consistent. I said I2 is going this way, right? Right? Is equal to I1 minus I2, correct? But did you notice that this IC is equal to CdV over dt? What does that mean about these currents? The resistors right here are they're affecting this current in the capacitor, right? Is that good? So I think what I'm going to tell you this, because I want to say we have a current going here, right? And we have another current going down here. Because I want to say that these are going to be in parallel. Does that make sense with me? Or to an extent? Let me show you. Because right now I'm trying to find tau. Okay, this is the important thing I want to know. Because let me start plugging and chugging. Right, so we have, what do you call it? Our V initial, right, is going to be 0, right? But our V final is going to be 8 volts, right? So VC of T, right, is going to equal, does it bother you if I do this? 8 volts, 1 minus, what do you call it? 1 minus e to the T over tau. Now we just got to figure out tau. Let me see. Because let's do our intuition. If this resistor right here, right, was in series with R1, right, we would add a time constant, correct? But these are in parallel, right? So that means, do you think our RC, right, or our total R, right? I'm going to do it on another piece of paper. This right here is page 6. Page 7. So what I'm trying to say is RC, right? We know what C is, right? But we're trying to figure out the R, right? So can we just say it's going to be R1 in parallel with R3? See? Is that good? And then what is R1? R1 is our 30K. And then our R3 is our, what do you call it? Let me see. Forgetting our numbers. Give me a second. R3, 60K, right? Times C. Now, what did we just calculated this to be? And then, let me see. I'm forgetting my numbers again. So 30 times 60 divided by 90, 20? 20K times what's our capacitor? Let's look at it. 100 micro. All right, is that good with everybody? And then we got kilo and micro give us milliseconds, right? And we got 20 times 100 gives us 2,000 microseconds. but this 2000 turns into 2 seconds, right? Is that good? Do we want to prove this? I want to prove this because I like being confident, okay? This is what I want you guys to do with your homeworks, okay? Because the last thing I want you guys doing is panicking and saying, oh, no, I don't know how to do the homework, or I need something to give me validation, or like, did I do it correctly, all right? So I'm going to do the following. I'm going to do this resistor right here, this resistor right here, this capacitor right here, right? This is what you guys are going to try and do in your homeworks. Voltage. Boom, 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 boom. All good? This right here was 30K. Does it bother anyone if I just rename it R3? 60K? 100 micro? Is that good? And this right here is our 12 volts. Is that good? Don't forget our happy little ground. VN, right? And I'm going to do this. Come on. Move. I'm going to call this VC. Is that good? Now I'm going to create an initial condition. .IC initial condition. The voltage of VC is equal to 0. Right? It's empty, correct? And I think we're good. Let's run it. And we said it was going to be 2 seconds, right? So let's run it for 10 seconds. Let's see if we got it right. Boom, baby. Well, that's a current. That's our voltage. Does that look good? Let's see. Let's verify. Let's verify, okay? I'm going to do the following. We just said V of t, right, is equal to 8, right? 1 minus e to the minus, or t over tau, right? But we just said tau is equal to 2 seconds, right? So that means if t is equal to 2, right? Right, 2? So that means it should be 1 minus e to the minus 1, right? Is that good? Right? Well, actually, okay, let me show you. I don't like skipping steps. This is page 7. Okay. Let's reiterate what we just did, okay? No more skipping steps. 8, 1 minus e to the, I'm going to punch in the answer, 2 seconds, correct? T is equal to 2 seconds, all right? 8, 1 minus e to the minus 2 over 2, right? Is equal to 8, 1 minus e to the minus 1. Is that good? What's this equal to? Calc. Let me see. 1 minus e to the, no, I don't like that one. There's no other way to do this. MATLAB. It's my favorite best friend. You guys know what MATLAB is? It's a calculator. Oh, that's the answer to another class's discussion. I'm going to do this. Or what do you call it? VC, right? It's going to equal 8, parentheses, 1 minus e to the minus 1, right? I'm going to put this in parentheses. You like my little calculator? Oh. There we go. 5.5 volt, 5.05. So we should be seeing 5.05 at 2 seconds. What do we get? Oh yeah, let's go. You guys feeling good? And better yet, let me show you the cheat sheet. So the reason why I was trying to show you guys that, like the LT spice thing, is because we were trying to figure out, okay, we have, what do you call it? We have the condition where we have two resistors, right? But they're both being dominated by whatever the current in this capacitor is, right? IC is equal to the current in this one minus the current going out, right? So that means these two currents are directly playing with this like differential, right? So what, and then we were trying to say, oh, are we adding the resistors? Are we putting them in parallel? They're in parallel, all right? And then based off that, our RC time constant is these two resistors in parallel and our capacitor. Boom. Is that good? But now what about our, what do you call it? Our actual current, I. Let's see. What do we have here? So I want to know the current in this actual what do you call it? Inductor, right? Or capacitor. What's this equation right here? That's our voltage right there at that capacitor, right? So let me see. I want to try and do something funny. Remember how I said it was equal to, how do I want to try to show you this? That's a good way to show you before time runs out. Well, this is IC, correct? Which is equal to I1 minus I2, right? But I1 was equal to this 12 minus this VC, right? 12 minus, let's just put VT, right? All over R1. Is that good? And then minus, we got this VC at T, right? Over this resistor. R3. Is that good with everybody? This is page 8. Let's do one more thing. This will be the last thing we gotta go do before we leave class. I of t, right? I'm trying to solve for that current, right? Is equal to 12 minus 8, 1 minus e to the whatever this right here, right? Remember that? That's the equation we just solved for over R1. Let me see. Minus at 8, 1 minus e to the minus t over tau, right? R3, right? Now just trying to solve for the numbers, correct? Let me see. How do I want to show you this? 12 over R1 minus 8, 1 over e to the minus t over tau over R1 minus, oh, I see something. Okay, I'm going to put that minus there, right? Because there's a minus here, minus there. 1 over R1 plus 1 over R3. Is that good with everybody? You like how I skipped that step? I have this right here and I have this right here, and it's a common term to these two. Is that good? 12 R1 minus 8 1 minus e to the minus t over tau. And then whatever this is in parallel. This looks like a parallel resistor, right? Right? Is that good with everybody? Do I want to solve that one? It's going to be equal to this. R3 plus R1, R1, R3. And then you'll have to solve for that manually, okay? But then let me show you the current. If you want the current, looks like this. Boom. Is that good with everybody? Any other questions before we end the class? All good? All right, y'all. Have a good day.